Very good. So hello, everyone, and welcome to today's webinar. My name is Katie Brickey, and I am the current chair of the American Society for Quality's Chemical and Process Industries Division. So the mission of the Chemical and Process Industries Division is to facilitate the interchange of ideas, tools, practices, and solutions necessary to address real chemical and process industry problems. To that end, today we are excited to host Dr. Caleb King, who will present a talk titled OofA, a survey of recent research in order of addition experiments. Now, before we begin, I'd like to take a brief moment to thank Stephen Barnett, our webinar chair, for all of his behind-the-scenes work to orchestrate this webinar. Thank you so much, Stephen. I'd also like to briefly mention that our division co-sponsors an event called the Fall Technical Conference that takes place in just a few short weeks, October 8th through 10th in Nashville, Tennessee. This is a wonderful conference that we're looking forward to, and you can find more information at falltechnicalconference.org. Now, I'd like to introduce our speaker today, Dr. Caleb King. Caleb is a senior research statistician developer at JUMP Statistical Discovery. He received his MS and PhD degrees in statistics from Virginia Tech, and his area of research is primarily in design of experiments. Today, he will discuss an interesting area of DOE called order of addition experiments. Now, on a personal note, I'll say Caleb and I were in graduate school at Virginia Tech at the same time, so I have known him for several years now. And I can say that Caleb is not only incredibly smart, but he also has a wonderful ability to communicate complex topics in a simple and engaging way. CPID is so glad to host Caleb today, and I know we are all in for a treat. Caleb has let me know that you can submit questions throughout the webinar using the chat feature here in WebEx, and we will have time at the end to answer these questions and have some discussion at the end of the talk. So with that, I will hand the floor over to you, Caleb.
All right. Thank you, Katie, for that awesome introduction. I hope I live up to it. And thanks again also to Stephen for inviting me to give this webinar. So I'll kind of start with a bit of some openness that when Stephen did initially invite me, I was kind of trying to decide what exactly would I talk about. My background's reliability and design of experiments, and I feel like a lot of people at CPID are familiar with that. So what can I tell them that might be a bit novel? And so we kind of shared some ideas back and forth, and I finally said, you know what, I've dabbled a bit in this order of addition experiments thing. I think it's kind of interesting. So I figured, why not that? So here we are, me trying to give an overview of some recent research in order of addition experiments, or OofA, as we kind of like to call it. And the best way I think to motivate this is to start with a story that I'm pretty sure we're all familiar with. And that is of the lady tasting tea. If you're familiar with it, you might, I hope you enjoyed this retelling. If not, well, hey, I'm glad you're here to hear it for the first time. So the way the story starts, our setting is Rothamsted Experimental Station over outside of London. It's more of an agricultural research place. And there was a psychologist there, actually, I think she's a psychiatrist, excuse me, one of the two, named Dr. Muriel Bristol. And she was taking a break. It had been a busy day. And so along came a colleague, Dr. Ronald Fisher, who decided to be a bit of a gentleman and offer a cup of tea. And she took a little bit of a sip. I was like, well, thank you, but I noticed you put the tea in there first. I actually prefer the milk first before the tea. Now, Dr. Ronald Fisher had prepared the tea outside of her view. So his natural response was, how, there's no way you could have possibly known that just from tasting the tea, the order in which I put that. To which Dr. Muriel, Dr. Bristol kindly responded, oh, I totally can. To which Dr. Ronald Fisher said, no, you can't. Yes, I can. No, you can't. And just before they burst out into a musical number to express their feelings, along comes another colleague, Dr. William Roach, who's like, guys, come on now. We're scientists. Let's do an experiment to test this. So Dr. Fisher was like, yes, let's do that. And they all agreed. And so what they did is they prepared 8 cups of tea. And there were 2 variants. So one variant had the tea before the milk, and the other had the milk before the tea. And they randomly arranged these and gave them to Dr. Bristol in a random order. And I'm happy to tell you that she got 100% accuracy on it. Now, at that point, I probably would have stopped. That would have been confirmation enough for me. Now, she knows exactly what she's talking about. Dr. Fisher decided to actually do a more formal statistical analysis. I'm pretty sure he came to the same conclusion. But yes, Dr. Bristol absolutely knew what she was talking about. She has apparently been drinking tea for a very long time. And of course, this is very famous. It was initially told in Dr. Fisher's book on the design of experiments. It's typically lauded as one of the first experiments designed by Fisher and analyzed using statistical methods. He might have done some before then, but this is definitely one where you have a combination of a designed experiment and statistical analysis. It also happens to be the first ever, at least to the best of my knowledge, recorded order of addition experiment. So it's quite interesting that the first experiment we kind of hear about in our statistics classes is actually an order of addition experiment. Now with that, what exactly do we mean by an order of addition experiment? Well, let's start with the experiments we kind of know about, what I'll call factorial experiments. Now, I know technically in design of experiments, the factorial experiment is a specific type of experiment. It's basically all combinations. We can usually talk about optimal designs and other things. Here, I'm going to refer to factorial as the nature of, well, I have some factors that I think affect one or more outcomes, so affect one or more responses. And the way I typically assess that is through combinations of settings. So typically with a screening design, think about that. It's high and low combinations. So I have a bunch of factors. I do a bunch of combinations of high and low settings. And from that, I can then estimate what I think the effects of each factor are on the response. Now, the way this is different from an order of addition experiment is that instead of the factor levels and the settings and the actual effects from the factors, we're more interested in the order in which factors are applied and how they affect the response. So typically, you would keep the settings constant. So in the lady tasting tea example, I'm pretty sure Dr. Fisher did this. He would keep the same amount of milk and tea, and all they changed was the order in which it occurred, whether milk before tea or tea before milk. So that is what makes it an order of addition experiment. Now with that, I'm going to go into a quick brief history of some of the research in order of addition experiments before we get on to some of the more technical details. So, as it turns out, this isn't necessarily a new area. You might have been hearing about it for the first time, and it might just be that you actually have done some of this. You just may not have heard of it described in this way. As it turns out, OofA experiments have actually been conducted for several decades, and most commonly in the biochemical and chemical industries, which makes sense. We're dealing with chemical reactions. The order in which you put in your elements is obviously going to have an effect on the type of response you get. So they'd been doing these experiments for a long time. You can look in the literature. In fact, some of the literature that people cite in the design papers that I'll kind of be touching on cite a lot of literature going back to the 90s, 80s, and so forth, where people were doing this. And of course, the lady tasting tea. However, in doing this, there had been no official research into, can we do this more systematically? Typically, it was, well, if I have a small number of components, I can do all possible orderings. Or I'll pick a random subsampling and hope I get one that kind of points me in the right direction. Or I kind of have some subject matter expertise into how the ordering is going to affect things, so I'll use that to inform my decisions and my experiments. But there had been nothing more formal in to say, can we actually create a systematic way to design these and even analyze them? And that all kind of changed in around the 1990s, 1995. At least to the best of our knowledge, that was the first time anybody actually looked into, can we create designs for this? Now, this particular paper was actually published in the ASA Proceedings of the section on Physical Engineering Sciences. I wasn't aware such a publication exists. I don't know if it exists anymore. But to me, that kind of says, well, Dr. Van Nostrand, what he did is he probably presented at the joint statistical meetings back in 1995 on this topic. He proposed some ideas of maybe we can use some existing designs and kind of reorient them to design and analyze for these order of addition experiments. And that got published in these proceedings. And that was it for the next 20 some odd years. Nothing came about from it. That is until about 2017, in which case Dr. Joseph Voelkel revisited this topic. Now, it wasn't formally published until 2019, but there is an archive version that shows it was around, he was looking into this around 2017. And he actually expanded a little bit more on what Van Nostrand was doing, which again, I'll go into details later. Um, he was a little bit more systematic with it. And again, proposed ideas of how could we design and how could we analyze order of addition experiments. There were a few little papers after that, and since then, the rest, as they say, is pretty much history. It's fine. This time, the topic stuck. And as a quick illustrative example, this is by no means an exhaustive count. This is based on citations and papers that I collected. And you can kind of see in 2019, 2020, it's starting to get there. By 2021, this has become pretty much an active research area. Okay, so there's been a lot of publications since then. There may be some correlation with a certain pandemic happening around the time. I won't try and speculate. All right, so that is a brief history, at least from my perspective, on order of addition experiments. I do find it kind of interesting. This is one of those topics that kind of came about as I was still learning. So I can remember attending even Dr. Vogel's talk on this topic, thinking it was quite interesting, hoping to see where it went. Shortly after 2020, I did revisit the topic and noticed that the number of papers grew quite a lot when I last looked at it. So that was quite exciting for me to see an active research area develop during my lifetime. So, all right, with that, let's get into the nitty-gritty details, or at least not too nitty-gritty. Now, at this point, I'm going to try and maintain a balance between high and low levels. I don't want to get too technical. I also hope I don't miss anything as I'm going through this. This is basically my approach to try and summarize some of the details of order of addition experiments. I'm probably going to move by model, because once you define a model, from there you can then infer how you could design an experiment to then estimate parameters of those models, kind of like what you do in optimal designs and other types of designs. So it's a little model driven. So that's the way I'll approach it. Again, there might be those listening in who said, I've done some stuff in here. Why didn't you talk about that? I am so sorry. I had only so much time to cover things, so much material. I'm just trying to cover the highlights. So that is my full disclosure, full disclaimer there. Please don't get mad if I miss something or don't go into as much detail. I do have a lot of references at the end. So if you want all that, I'm happy to offload that to you. Let's start with some basic foundational material. So I'm going to let M here represent the number of components. So we usually talk about it in terms of components rather than necessarily factors. And this probably has its origins in the chemical industries and such, where we talk about components and maybe a mixture or a process. So again, we're going to use that term component and factor. I might use them interchangeably, but typically when I talk about a factor, I'm thinking more in terms of I'm going to change settings of a factor. When I say component, I'm actually just putting it into a sequence. Okay, so we have a number of components in our experiment. Now, the most obvious starting point is, why not do all possible orderings? I mean, that's the way we initially did experiments at the beginning. Now, of course, there we clearly saw that as the number of factors you put into a design grows, the number of runs grows exponentially. Similar idea here, but much worse. You see, as M grows, as the number of components grows, it doesn't grow exponentially, it grows as the factorial. So M factorial. And just to illustrate that point, here's a little table. So on the leftmost, we have the number of components or factors. So if I think of a standard screening design, 2 levels per factor, you can see it kind of grows. There's that exponential growth that we're starting to see. So about 6 factors, you've already got 64 some runs. With an order of addition experiment, you initially see we start off, we actually get away with less runs, but that's the only time where the factorial kind of beats us out. After that point, the order of addition, the OofA experiment grows super fast. By the time we get to 6 components, you would need over 700 runs to just do everything. Don't even talk about 10 components. We know for full factorial, that would be 1,000 some runs. That's already big. OofA, don't even bother. It's millions. It's off the charts. So you can clearly see that the growth problem is even worse with order of addition experiments. So it's really important that we try and find, can we do this in a much smaller number of runs? And so with that, let's move into our first type of model that was proposed. So the first model that was proposed, this is what Van Nostrand did, Joseph Vogel, and it's sort of been the basis going forward, is what's called a pairwise ordered model. Here, our factors, if you will, are pairwise terms. So here I have a simple experiment with 2 components. So I'm just going to say is one, think of the lady tasting tea, milk before tea, tea before milk. In this case, I can describe it using one factor. I call it P12, P for pairwise ordering. And essentially it says if 1 comes before 2, this is a positive or a +1. I'm being very skippy on my notation, so plus means +1. If I reverse it, I do -1. It could technically be 0 if you applied both at the same time, but typically it's plus or minus 1. So you can see some relations to factorial type designs, if you will. And so essentially what it's saying is my expected value for my response is some mean value, and then that increases or decreases based on which order certain pairs occur in. So for the simple 2 component, it's just is 1 before 2 or 2 before 1. Does it increase or decrease based on that? Here's another example using 3 components. Here we actually have the full combination for 3 component runs, so there are 6 of those. And you can see again that it's very simple. All you have to do is say, okay, here's P13. Does 1 come before 3? Yes, yes, yes. No, no, no. Okay, so if it goes the one way, it's +1, minus if it goes the other way. That is the pairwise ordering model. Okay, and you do this, so there's going to be M choose 2, number of these factors, because it's looking at all pairs that are occurring. Now, something I want to point out here real quick. You'll notice that this looks almost like a full factorial design if these were the 3 2-level factors. But there are 2 levels missing, 2 runs missing. And that's because under this model, there are actively some constraints, disallowed combinations, actually. Let me give you an example. So let's look at this run. So this is positive. That means that 1 comes before 2. This is negative. 3 comes before 1. If this were positive, then 2 needs to come before 3. So that would mean 1 comes before 2, 3 comes before 1, but 2 comes before 3, which should come before 1, which comes up. I've created a loop. Now, obviously, I can't apply a sequence in a loop. Maybe in some places I could, but generally, no, you can't do this infinite loop type behavior. So that is a disallowed combination. This is forced to be negative in order to be an actual sequence. And so that actually influenced how some of these initial designs were created. People recognized that there were these constraints present when you used the pairwise order model. And so we need to account for that both in our estimation of parameters, our actual model fitting, and in the design. So for example, when creating those designs, some of the early attempts essentially started off as take an orthogonal array, that's something we know, and then maybe I'll enforce these disallowed combinations into them, adapt them to these constraints into the pairwise order model. Maybe that's a good start. That's a pretty good start. And so that's what Joseph Okel and Van Nostrand were kind of doing. Shortly thereafter, Jayu Peng, Rahul Mukherjee, and Dennis Lin. I apologize if I butcher anybody's names. I am so sorry. I'm going to do my best. Shortly after that, they took this concept and they ran with it. They actually, in their paper, developed an entire optimal design theory for OofA experiments based on this pairwise order model. So they were able to show things like the full design achieves D, A, and E optimality. And they were able to show how that works. They were able to sort of create a function showing you what that D-optimal criterion would look like under those designs. Another thing they showed is that if you have a smaller design that achieves the same moment matrix as the full design, then whatever optimal design properties the full design has, you get for the small design. What this means is that if I can create a small design that has the same moment matrix as the full, if I want a D-optimal design, that's an easy way to do it. I say easy in quotation marks, because obviously it's going to take some work to find those moment matrices for smaller designs. But it gave us a standard by which we could work off of, and we could start creating these designs from. So in fact, much of the early work focused on what are called OofA orthogonal arrays. Essentially, these are orthogonal arrays where the ratio of frequencies amongst certain combinations in the fractional design, so the smaller design, fraction of the full ordering, matches those in the full design. So that was sort of the standard. If I can find something that matches properties in the full design, I'm golden, especially if I can do it with smaller run sizes. And a lot of the construction algorithms, I'm not going to go into detail here, not enough time, but usually involve some special building blocks you start with, or it's sort of sequential construction where I can start with a previously known OofA orthogonal array and use it to create larger ones. Or if I can't necessarily get an OofA orthogonal array for my particular constraints, I'll get close enough. But at least we had a standard by which to work off of. So here's an example of what that might look like for 4 components. Now the full factorial, the full design for 4 components would involve 24 runs. This one involves only 12. It is de-optimal because it has the same moment matrix as the full one. So this is a nice special case. Now, they have shown that this can only be achieved for certain run sizes, kind of like with orthogonal arrays and factorial designs and standard DOE. Only for certain run sizes do you get all these nice, wonderful properties like orthogonality and such. Same type of idea here. But this is an example of what that kind of looks like. You'll notice some runs missing. So for example, there's no 4, 3, 2, 1 here, but that's okay. This design will allow you to estimate the pairwise order model pretty efficiently. Now, since that model was proposed shortly thereafter, and by shortly I mean within a year pretty much, a lot of this research took off pretty quick. There were some variants proposed. One of the earliest ones was in 2020 when Robert Mee proposed a triplets order of addition model. This is essentially a pairwise order model that has interaction terms in it. So he looked at it and said it would be nice to include some of that because sometimes if you just look at what are essentially the main effects, those main terms, that may not be flexible enough to account for what's going on in the data. So we can include these interactions, but you have to be careful because of those constraints. So essentially, motivated by what happens in mixture models for mixture designs, you can take a similar type of approach when you do the interaction models here. Another variant that was actually proposed in the paper by Peng, Mukherjee, and Lin was called a tapering pairwise order model. Now, in the standard pairwise order model, you'll notice it didn't matter where in the sequence, say, 1 before 2 occurred. It could be right next to each other. It could be at the end, first and last parts of the sequence. But all it cared about was, did 1 come before 2? In the tapering model, you actually count for the distance between them, because that could also be informative. Yes, 1 comes before 2, but if it occurs further apart, that might have a different effect than if they're right next to each other. So that's called a tapering model. So they tried to include some terms that you could multiply by the factor levels to kind of scale it based on the distance between terms in the sequence. So those are some quick variants I wanted to highlight there. Now, again, there was a lot of active research going on here. So again, not too long after the pairwise order model was proposed, there was another model proposed. Again, by too long, less than a year, really fast. This new model was called the component position model. It was proposed by Zhenfeng Yang, Feixing Sun, and Hongquan Chu in 2020, but formally published in 2021. Now, the best similarity that I can give you for this type of model is essentially the cell means model from ANOVA. Think of it kind of in that light. In that this case, instead of looking at the relations between pairs, I'm actually looking at if this component is in this position, what is its effect on the response? So again, let's look at that 2-component example. So this is what the component position matrix, not exactly the matrix, but the type of factors would look like. So the subscript tells you the component we're looking at. The superscript is going to tell you the position. So this is essentially an indicator saying, is component 1 in position 1? 1 if it is, 0 if it's not. Is component 2 in position 1? For here it's not, for here it is. And so on and so forth. One of the things you'll notice is this model is over-parameterized. So there's definitely a lot more terms that we need to estimate than we have runs to do it. So there are additional constraints, different types of constraints now that need to appear. So certain terms that can't necessarily appear in the model, similar to what you might see in ANOVA or cell means model type situations to account for that. The trade-off is that you have a lot more flexibility in what you can do with your model, because now your input is the actual position. So you can actually see if I put a component in a certain position, it doesn't have to be relative to anybody else. It's just saying if it's in this exact position, what effect it has. So you get a little bit more flexibility with your approach. In terms of the designs, it's also led to a slightly different type of design, which is called a component orthogonal array. In this case, the arrays are defined not in terms of what happens in the full model, but sort of similar to, it's sort of a generalization of the usual definition for an orthogonal array. And it's all related to the positions. So there are 2 rules. The first rule is that each component needs to appear in each position equally often. No component gets to hog that first position more than anybody else. It's distributed equally. Everybody gets a chance to be in every seat. essentially. And then for any two components, each possible ordering, so I before J, J before I, appears the same number of times within any combination of positions. That's a mouthful. That's a lot to unpack. I'll show you what that looks like on the next few slides. It's essentially that same idea. If I've got two components, their ordering is going to be visiting all the possible combinations, positions, and orderings that you can do. Everything's nice. Everything's balanced. That's the basic idea. And again, a lot of the construction related to this was similar. You could start with some basic building blocks. A lot of that was Latin square designs or other types of similar structures, including previous component orthogonal arrays. Quick shameless plug. If you want an example of this in 2024, I and some colleagues published a paper kind of looking at how you can do this using Latin squares to sequentially create these designs, maybe as a way to actually analyze them before you have to go through the full design. Again, shameless plug for my paper there. But again, that's a kind of example of how you can build these up. So again, here we have an example of component position. Now, what you might notice in the literature, for a lot of small numbers of components, usually component orthogonal arrays have good properties for pairwise order models as well, if they're not exactly the same type of design. In some cases they are, but not always. But they generally, pairwise order models and component orthogonal arrays, they didn't have good properties for each of the other models. They're not too far off from each other. They're not vastly different designs usually. So here's an example for components. Notice I don't have things compiled in a run. I've got them spread out. This is a position matrix. What it means is that each column is the component and the entry tells you the position it's in. So for example, component 1 is in 1, 2, 3, 4. Now the way I've labeled it, you can essentially read off where the component's going to be. So let's look at what makes this a component orthogonal array. Let's first look at those positions. Again, each component should appear in each position the same number of times. Component 1 appears in the first position 3 times. So that means component 2 better be there 3 times, which it is. Same for component 3, same for component 4. Quick another example. Position 2 here, component 1 is in position 2 3 times. Component 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. All right. I won't go through all of them, but I hope you see that's exactly how you would evaluate that first one. So everybody's balanced in terms of the number of positions they're in. The next thing we need to look at is let's pick a pair of components, about 1 and 2. That works. And they should appear in all, so those pairs in that order should appear in each position. So I've highlighted that here. So component 1, there are 3 options where component 1 is in the first position. Component 2 should be in 2, 3, and 4. If I move component 1 to position 2, there are 2 options because it can't be in position 1. If it is, I've switched the ordering. So maintaining that order, component 2 is in position 3 and 4. And if I put component 1 in position 3, component 2 better be in position 4. So that order, 1 before 2, appears 6 times. If I were to switch it, 2 before 1, you can see there's 1, 2, 3, 4, 5, 6. So that's the basic idea there. If you pick any 2 columns, component 1, component 2, component 1, component 3, you should be able to pick out as you move down that, okay, for that particular order, they're in all the possible positions there. I'm not missing anything, or I'm not doubling up on a particular order. So again, that nice balance should be present everywhere. All right. Now, one of the advantages of this model is that it can actually be generalized further. So Zach Stokes and Han-Guan Xu generalized this to allow for interactions and even polynomial order models. How did they do that? Well, you can revisit that model, but now generalize it further and just use this general expression. B is the position matrix. That's this guy. This is the position matrix. Okay? That records the position that component falls in the sequence in each run. And then I have some vector of basis functions that are a function on a row. So take one of those rows where the entry is the position of the certain component. Okay? And what are examples of what this might look like? Well, we've actually already seen some. If you use as that vector basis function, if you use as the basis function the sign of the difference between the positions, that's the pairwise order model. So this general form accounts for the pairwise order model. If I use it as a sort of delta function to just say, is it in that position or not? That's the component position model. So you can generalize it even further. In fact, what they did in their papers, they considered 3 more models, 3 orders of models. These are based on suggestions that were actually made by 2 authors previously, Christine Anderson Cook and Lou Liu. There was a review paper early on about this whole order of addition experiments thing, and they invited some discussants. And in one of those, Christine Anderson Cook and Lou Liu proposed maybe you could use polynomial order models to analyze this. They didn't go into detail. Zach Stokes and them took that and provided that detail. So quick overview, what that looks like. Here's an example of a first order. So again, there's the position, and then you got some orthogonal polynomial. I'm not going to show the formula here, but you can look that up, pretty standard. So there's a first order polynomial here. So that's a first order model. That's going to be very similar to stuff that we've seen previously. Quadratic, so now I've got a first and second order polynomial, so now I can include some quadratic effects, and then I can go full second order and include interactions as well. This is just an example of the generality of this type of approach. So just a quick example there. All right. Now, at this point, we're going to make a bit of a transition, because up till now, we've only considered the order in which components appear, which seems, why would you point that out, Caleb? That's the whole basis behind order of addition experiments. We only care about the order. Technically, yes, but in practical terms, order isn't the only thing that matters. In some cases, it's not just the order, but how much of a factor, let's say, especially in mixture experiments. Think of a mixture experiment. I'm going to mix things together. So I can keep things at the same level in the ordering, and that counts for some of it. But what if I change the amount now? That could definitely impact the outcome. Is there a way then that we can create experiments that account for not just the ordering, but then now the factor levels? And that's what we're calling an OofA factorial experiment. Now we're going to go back and include those levels. The earliest work on this was in the area of mixture factors and mixture models. And so there they generated optimal designs using a thresholding algorithm. And this made sense to start here because it was very close to sort of the origins of order of addition experiments. So with mixture components. Shortly thereafter, in fact, since then, there's been a couple research articles that are trying to generalize this now to the more standard factorial designs we're used to. In this case, we're still looking at 2-level screening designs, again, that we're looking at for the factorial side. Most of the research I've seen, and again, if you're doing research in this area and this doesn't sound like what you're doing, I'd love to know. This is what I've seen so far. Their models have essentially a factorial component and an order of addition experiment component. There's no interaction yet between the two. They're not accounting for cases where, well, the way this factor affects the response when I change the settings could change depending on what order it occurs in the sequence. There's nothing I've seen yet about that. That's an open research topic. There's also a big open research topic is, how do I make designs with this? Because the standard approach is, okay, let me give an example. I have a 12-run factorial design to account for the factorial part. I have a 12-run, so I got, say, 4 factors, so I did that in 12 runs. And I'm going to have a 12-run order of addition experiment side. If I just do all combinations, that's 144 runs. That's already big. Okay? That's what we currently have right now. Most of the early attempts are trying to say, can we do better? Can we improve over just this Cartesian product of the designs? So again, that's an open topic right now in terms of the research that I'm seeing. Can we do better than that? It would be great if we could. And finally, what other additional models have been proposed? So the 2 I've talked about are the standard ones, the 2 most popular. Now, Hans-Peter Piepo and Emmeline Williams did sort of a brief survey of some of those and other models they proposed. It turns out there was so much research going on at the time that by the time they had proposed some of those models, they actually just ended up being minor variants of models that were already published. So it was really fast. But again, they did some comparison and they kind of showed there wasn't a clear winner in terms of the models. It really depended on what you were looking at. But there are little tweaks you can do. One that is definitely different from the others is the Gaussian process model. This was actually proposed early on. It was called a Kriging model, same type of thing. So this was proposed back in 2021. It's been sort of revisited in the context of OofA factorial designs in the most recent paper this year. But this definitely has some promise because Gaussian process models are quite ubiquitous now across all areas of statistics. So this might become a third contender if there's enough interest in getting that going. Okay, I just threw a lot of information at you. Your head is probably spinning and what the heck is going on? Let me walk you through a quick demonstration of how you would use these models. I'm not going to focus too much on the design aspect of it because, again, I can refer you to the papers on how to construct the designs. The examples we're going to use, the designs are pretty good. But of course, if you want to know how to design it, it's really good to know how would you actually run these models and interpret them. So with that, I'm going to use an example that's used by multiple articles and as motivation for analyzing this type of data. It consists of 5 components. We're going to apply them in a sequence. In this case, these are 5 drugs that were applied in 2 batches. So we also have an extra batch effect that we need to account for. And that's not too hard with these types of models. So here's the data. I adapted it. I copied it out from Robert Mee's 2020 paper, rearranged things a bit, mainly so I could highlight some things for you. So I've tried to present them. We have block 1 and block 2. I've grouped them by what is their first component. So I've tried to organize them, sort them in order of the sequence. One thing I will kind of highlight if you scan through this data a bit, when 3 is the first term, you get a lot of high values. In this case, we have a response we want to maximize. And it's interesting to note that when 3 is in the first position, you typically see most of your high values there. Maybe 5 is the next biggest one, but that was something interesting that kind of caught my eye. So let's take note of that as we kind of go through. So a brief look over the data can give you a hint at what might be a good sequence. But again, the benefit of these models is that we can actually throw it in, analyze, fit a model, and the model could actually tell us a sequence that we didn't see that is better than anything we did see. It also can account for the noise. Okay, so let's look at the first model, the pairwise ordered model. This is a pairwise ordered model with interactions. It was taken from Robert Mee's paper, so of course it will have interactions. Let me walk you through how you might interpret this type of model. So I've highlighted a couple terms. These are terms that were either just statistically significant or definitely were. They're kind of the main drivers, but he included all of them. I'm going to include all of them. I'm not going to take away from what was presented there, but I do want to highlight some things. So of course you've got your intercept, your main mean value essentially. We have a batch effect. So apparently in the second batch, things weren't as good as in the first batch. If we want to maximize our response, the way we do that is kind of as follows. We follow through the terms. What this is telling us is if you want to maximize your response, 5 should come before 1 because this is negative. And it's negative kind of big. So if we switch it, now we get that boost. 3 should come before 2 if possible. If so, we get a boost. If we need to have 5 before 2 as well, we get another boost. And this is kind of saying you get a small boost with 2 if 2 comes before. But this is basically saying, ideally, let's put 5 before 1 and 2 somewhere in there, and 3 before 2. And if we put 3 before 4, we get another boost. So 5 should come before 1 and 2, 3 should come before 2 and 4. So we kind of get a wide array of sequences that could satisfy that criteria. Now let's get into the interactions. These are interesting. Essentially, this is saying, well, if 1 comes before 3 and before 5, you get a kick. You get a dent in your response. So I need to break that up somehow. Maybe I can put 3 before 1 and 1 before 5, or vice versa, 5 before 1, 1 before 3. If I do one of those, that might kick this sign to the other side and give me a boost. This is saying if 1 comes before 2 and 5, I get a boost. And if 3 comes before 4 and 5, I get a boost. So now the trick is, how do I combine that with everything I just read through previously? That's the tricky part. That's something that we could probably let the model do. If we do, what it says is that the best sequence is 3, 1, 5, 2, 4. So 3 is coming before 1, which is coming before 5. That flips that sign, so we get a benefit from that. We do lose out a bit here, so we get a little kick, but 5 does come before 2, we get that benefit. 3 comes before 4, we get that one. 3 came before, so basically we do get a kick from one of these terms, but there's a bunch of terms that have flipped sign that benefit us. Okay, that's one way to kind of approach it with this pairwise ordering model. Okay, so I hope that was relatively easy to follow. I know it was a little difficult. Let's look at another model, the component position model. Benefit of this model is you get a nice graph to go with it. This is called a component position effects plot. I took this straight from Ingedal's paper. Now, I do have to warn you, for some reason, they decided to use zero-based indexing instead of one-based indexing. So this is actually the same as component 3 that we saw previously. So whatever number you see, add 1, that's the component we're talking about. Now, if we just read off this plot, what it's saying is, so if I put this component in that position, this is the average response I get when that happens. So this is saying, hey, if you put component 3 first, you get a very high mean response. That's good to know. That seems to imply component 3 should definitely be somewhere near the front. This is component 5. It gets highest when it's in the second position or first position. So clearly we get, we want 3 or 5 somewhere in the top. This is component position 2. That's a little bit further down, so maybe it's good if it's there. 0 and 1 are here. That means 1 and 2. So maybe we can put 2 there, 1 there. Component 4 gives you the best response if it's all the way at the end. Notice everywhere else it's either in the middle or at the bottom. So definitely the further down in the sequence component 4 is, the better you're going to get. In fact, you could technically read this off and say, well, I think based on the model that the best sequence might be 3, 5, 2, 1, 4. Let's keep that sequence in mind. Let's actually go now to the model. How would I interpret this model? So I've done my model fitting. I've gotten my estimates. Again, there's a mean term. I've got a batch effect. It's negative like it was before. There's consistency between the two models. Here, there's a slightly easier interpretation. What this is essentially saying is, okay, if component 3 is in the first position, I get this bonus. If 5 is in the first position, I get this bonus. They're comparable. Okay, we saw that in the previous plot. If 3 or 5, again, zero-based indexing, 3 or 5 is in the first position, that's actually the best. That's actually some of the highest values we've seen. So 3 or 5 should definitely be somewhere at the front. Interesting thing is that the next two terms kind of complement that and say, well, if you did 3 at the first position and 5 in the second, you would get these two bonuses together. Okay, that's about 14 and a half, 15 bonus. If you did 5 first and 3 in the second, you get a bigger bonus. Okay, great. So that definitely confirms in the model that 3 or 5 should be the top two. You might get a slight benefit if you have one versus the other. And then this term is kind of saying, this one is definitely what we saw earlier, where the fourth component should not be first. Because if you do, you get a dent. You get a ding to your response. It takes away. So as long as component 4 is not in the first position, we're okay. That gets zeroed out. We're good. Don't put 4 anywhere near the first position. And this is a little something extra term saying, well, if 5 happened to be 3, you get a little bit of a bonus, but technically we should have it in one of the first two positions. Now let's look at the interactions. This is where things get interesting. Because what this is saying is, well, if you did do component 5 first and component 3 second, if you pick that one, I'm going to ding you for that combination. If I look here, essentially what it does is it zeroes out this contribution. So it's saying I get a bonus, but then I get immediately zeroed out because I put 3 in the second position. So technically I could avoid that, but by not putting 3 in the second position, in which case this would get zeroed out, but so would that one. If I did put it, this is essentially the contribution I get. And this is saying, well, if you put the 5 in the second and 4 in the first, you get this bonus. But we have already said don't do that because then you get dinged this amount. So that kind of negates that bonus. So of this, my conclusion would essentially be put 3 first, 5 second, you get essentially a 15 value bonus to the response. A lot of these zero out because I'm not following them. And so that tends to give me the biggest net bonus. In fact, for this model, the best sequence is 3, 5, 2, 1, 4, which if you recall, is what you pull from here, 3, 5, 2, 1, 4. And not always like this, but in this case, this is a bit of a bonus to the component position model. You get a nice graph that helps explain things, and the terms a little bit easier. But I don't want to fully ding the pairwise order model because there are situations where that one could also be as easy to interpret as well. This just happened to be the example that I used. All right. Now, we've gone through some illustrations of how you use the models, some of the technical details. Who's actually using this type of stuff? Well, I've already mentioned one area, and that is the chemistry and biochemistry. So here's a sampling of some of the articles um, that people have cited in their design and the OofA design papers as kind of illustrations of who's using this. So chemistry and biochemistry, again, makes sense. This is clearly an application area where they would be interested in this type of stuff. Some other ones include pharmaceutics and the genomics industries. Some ties to the biochem fields as well, so that makes sense. But they are, again, also interested in these types of order of addition experiments. And then again, a lot of these, I've tried to organize these in terms of years, so you can see some of the 90s before even the official research into design of these experiments and the models came out. People have been doing this for a while. So they've been dabbling in this area for quite some time. Food science is another area where, again, related to that biochem and chemistry, so there's a lot of branching out from there, where people have been using the order of addition types of experiments in their applications. Now, these next two are kind of newer areas, at least in my view. So the first one is kind of this idea of scheduling and queuing theory. In other words, we're moving away from sort of the chemistry applications to maybe I've got some manufacturing process where I have to do things in a certain order. In this case, I could conduct an order of addition experiment to determine, is there an optimal way to do that where I can minimize time or maximize production quality? So those types of things were more recently proposed in some of the more recent papers. There's also other areas that kind of relate to this: logistics. I'd say even maybe some travel. Sounds weird, but if you've heard of the traveling salesman problem, I think there was at least one paper that mentioned this, where you've got someone who needs to visit these places in a certain order and they'd like to do it to minimize time. It is a known NP hard problem. Basically, there's really no easy general answer, but you could think of maybe applying order of addition experiments there to get you in the right direction, to try and get a fast approximate answer, even though you might not be able to get the exact answer, but it can get you there pretty quick. So that could be another application area here. Who knew you could apply statistics in the travel industry? The most recent field that I've seen this come up is in information theory, specifically with Shapley values. Shapley values were created as a way to kind of measure sort of the input that someone brings to some process. It usually is done as sort of a combination of, okay, if this person or individual or thing was present versus if it wasn't, what's the change in information that happens, or a change in some value. Again, it kind of came from economics, and I apologize if I'm totally butchering the description. But it's seeing some uses, not just in economics, but even in machine learning, where if you have this black box algorithm, you may not be able to look into the actual terms themselves to determine the effect, but you could do this idea, well, if I were to leave one out, have it back in, what's the change in its effect that way? That's kind of what the Shapley value is trying to do, average over those combinations. Recently, I've seen things where factorial designs have been applied to that, but you can also see through this paper that order of addition experiments could also be used, especially if there is sort of a process nature to how you compute the Shapley values. So we're starting to get into some more novel areas with this. Okay, with that, I'm going to start wrapping up here. So overall summary. Even though there's been a lot of recent research in the design of OofA experiments and some models, they've been used for decades. So it's been around, there's been a lot of use. We're only just now getting into, can we be more systematic? Right now, the two most common models are the pairwise ordered and component position. There have been some attempts to get Gaussian process models into the mix, so there's still opportunities for research into that. And the two areas where I kind of see most of their most recent research is in that combining of the order effects with the factor effects. And in my view, it's about dang time because for a couple of years now, we've only focused on the order. I've always been thinking, what about the actual factor levels? Once you get that information in there, then this will really take off in terms of practicality, my personal opinion. So I think there's still ample room for improvement here. Again, so far I haven't seen a lot of models where they interact, the order effects and the factor effects interact with each other. I've also seen some attempts at trying to get around the direct products of the design matrices. So if there's a way to do that a lot faster, that will really help this take off. And of course, there's still room for novel applications. We've already seen information theory was something that probably a lot of people didn't realize order of addition experiments could be used in. I think there's still ample room for other novel application areas. So with that, I'll just say, OofA experiments, they're here to stay. The research field is wide open. Take a look, see what you can find, see what you can do. There's still plenty of opportunities to help move this along. And with that, I will stop for questions.
Thank you so much, Caleb. Excuse me. Thank you so much, Caleb.
Sure.
I don't know if you can see my
Yes.
reaction. Everyone, you can join me if you have your WebEx emojis, giving Caleb a round of applause for this very interesting talk, very thorough. Appreciate all of your comments.
Sure.
If anyone has questions or comments or reactions, anything, please feel free to put them in the chat. We do have one currently that I'll read to you, Caleb, to kick us
Okay.
off. Question from John says, can you block for the first position? For example, if water must be the first component, or he follows up and says if water or ethanol must be the first or second component, so you have some restrictions on the ordering.
Right. I don't see why you couldn't. I could see in both types of models where you could make that either essentially that becomes a fixed constraint on it. Okay, you fixed that. You can make that a block. I don't see why that wouldn't be possible. Essentially, what you've done is now you've reduced the number of components that you get to play with. So if one or two of them essentially have to be in the first position, that could be one approach. Is okay, that's my block, and now I just get to reduce my design space essentially.
Sure.
That's off the top of my head, but again, I don't see. We have every recent example where we had an external block added in. There's no reason to think that if some of the components have to fit a certain order or you have other constraints that you can't incorporate that. So I would say both of these models could do that.
Very good, very good. Thank you, and thank you for the question, John. If anyone else has a question, please put it in the chat. I was going to ask you how do you say, application question.
Yep.
When you described the component position model and you showed that nice graph that you helped us read, is that how was that analysis executed? Do you know? Was there an R package or something like that to create that graph? I always struggle, thank you so much for walking us through the models, because I always struggle with what does this mean? 1, 3, 5, sort of
Yep.
like interpreting.
So I think there might have been an ARC package they used in that paper. I can double check afterwards. I imagine there was some sort of ARC package they might have used. But essentially, any software, all you have to do is once you've got that position made responses, all you're doing is just averaging over. So if the component's in this position, average over that and plot
Okay.
it.
Yeah, yeah.
I even considered putting the data into Jump and making that exact same plot.
As you
I wouldn't
should.
be able
I'm just
to,
kidding.
yes, I wouldn't be able to analyze it just yet. It doesn't
Yeah.
have that capability, but that type of plot, I think
Okay.
they probably just did it in R. I don't think they use their own custom software, as far as I know.
Yeah, very good. That makes sense though in terms of, sort of how it was generated.
Katie, I
Another.
have a
Oh, go ahead.
some. I have a couple. I
Stephen,
have
go
a
ahead.
couple of questions that have been messaged privately to me.
Oh,
Um,
perfect. Go ahead. Yes, please.
this is a kind of three-part question
Okay.
from Victor Caleb. Would it be possible to create designs involving factors levels and components order by one creating separate designs, as in 1 factorial for factors level, 1 for components order using arrays or Latin hypercubes, and then 2, do a Cartesian product of the two design matrices to create a candidate set.
Right.
And 3, to use this candidate set and select the most informative runs using some optimality criterion.
That sounds as good as any approach I've seen. You should write a paper on that, maybe. Yeah, at this point, it's anything you can do. So I mean that sounds like a good approach to me, or at least as a start of one. So yeah, again, there's a lot of open research in my opinion related to that. So something like that could be a good start. I know there are also in creating the order of addition experiments, there are some that use the search algorithms to do it as well. So it's not unheard of. It'd be nice if you could construct them using the basic building blocks, but there's research out there that basically says we can do searches for this. So what you just described, I would say fits in there, and it sounds reasonable to me. So.
Okay, cool. And then one other question Mark asked, do you do the OofA first before level DOE or reverse?
Maybe we should conduct an OofA to determine that. But there you go. Let's get meta on this. Ideally, I mean, you'd want to do them separate. It kind of depends on the situation, which is going to be more important. I could see, depending on the process, where you could do the order first, just to determine if that's going to be an impact. Because after that point, once you determine the order, then you could do the factorial piece, figure out how to combine the two. This is just me spitballing ideas. So I hate to give the standards answer out. It depends, but it kind of does, because it's really, which do you think is going to have the greater impact? Changing the levels or changing the order in which things occur. And again, ideally, if you can do both, great. But if not, you got to think about which is going to have the greatest impact, or which you have the most concern about. In my view, if there's any chance that the ordering could affect it, I might consider that first, just because we can get that out of the way, so that if ordering doesn't have an effect, I could then potentially use some of that information. I've got some runs essentially that I could borrow from that to maybe feed into the factorial design. Obviously, they're all at one level, so they're not going to by themselves tell you anything. But you could essentially say, if I'm going to run a factorial design now, I've got some runs where they're all at some low setting. Maybe I could kind of borrow that in here. So that's my thought.
Yeah, that's really interesting. If order doesn't matter at all, you could have 12 runs. I mean, at I don't know, center point conditions, low conditions,
Pretty
or
much. There you go.
whatever amount you've had. So that's,
Yep.
that's the study into your reproducibility or something like that.
There you go.
Any other questions that came to you, Stephen?
Nope, that's all.
Okay, very good. There was one more in the chat, sort of about software. I'm going to broaden this to say, do you know, or what do you know about software capabilities, both for design and analysis of order addition experiments?
That is an excellent question. So I don't know if there's any particular software. So there might be some custom software that people have used. I do want to say that I think there are some R packages out there
Sure.
that are doing this. And I think that's where most people are kind of starting to dabble, is creating that. I know at one point there was a little bit of an add-in for Jump to kind of help create some basic order of addition designs, but we haven't done too much further on that. I'm looking at the chat now. There's a question about Minitab. I have no idea, but I wouldn't be surprised if Minitab did have something. I think it's still a bit at the time where we were kind of looking into this. It still seemed a bit early in terms of what kind of designs are coming out. A lot of the research was still fast flowing. And so now that it's kind of, in my mind, started to stabilize a little bit, you might definitely start to see more of this come out in some of the software, especially if we start to see a lot more applications and people call for this.
Right. Yeah.
So that's my 2 cents on it.
Yeah, very good. Thank you. When I have looked at these type of experiments, a lot of it is sort of looking at the designs that are published, in the literature. But very good. I see actually go ahead. Who was that?
There was one more question from Tammy. Does this take into
I missed it.
consideration? That's okay. I think it was sent just to me.
Okay.
Does this take into consideration lot-to-lot variation in components? I have not seen that yet, so I haven't seen any sort of split plot type designs with this. That right there is another open research opportunity. Again, we've only seen right now block effects, so there's still ample opportunity to expand on this. But it might be pretty straightforward. There was the inclusion of a block effect, so once you have lot-to-lot variation, it's essentially, again, what type of model do you want to use, and then you include into that the lot effects, and then split plot effects those type of effects. So I could see that being pretty straightforward to kind of implement. Where the difficulties might come is, again, how do you specifically analyze it? But again, I still think that's ample research opportunities right there. There's still a lot we can do in terms of these models.
Very good. Exciting time for OofA enthusiasts. Very good. Well, thank you, Caleb. Thank you, everyone, for attending, for your questions, and especially thanks to Caleb for the interesting talk. We appreciate it greatly, and we look forward to seeing you all at our next webinar, which is not scheduled yet, but look for information from CPID for more fun coming later this year.
Now, is there a place where they can, where I can upload my slides if they can access it? Because I've got a lot of references here I'd like people to read. So.
Yeah, very good, very good. Stephen, are we able to email attendees?
I believe so. Let me look into that, and if that's not an avenue, we'll find an avenue to get it out to people.
Sounds
Okay,
good.
very good. And I will put my email in the chat. So we'll work on getting slides and recording to those who have attended. We're also going to upload it to CPID's channel in My ASQ for those of you who are ASQ members. But if you're not, that's okay as well. But if for some reason you're very interested, please feel free to send me a note and I can get it to you directly, for those who are very interested, because Caleb, like you said, has a lot of great references here. Very good. Thank you.
Thank you.